Today we're going to be talking about section 3.2 in your textbook, Properties of Determinants. So if you'd like to follow along in your textbook, you can do that, and I'll be posting this PDF on Brightspace. So recall our last video, section 3.1, we talked about what is a determinant, and we ended section 3.1 talking about if A is a triangular matrix, then the determinant of that matrix is just the product of the entries on the main diagonal. So just as a reminder, what does a triangular matrix look like? If we have a matrix and we have maybe some numbers on the diagonal, who knows what they are, then up here can be anything that you want, but down here is all zeros. So if we have a matrix looking like this, then our determinant of our matrix is just going to be the product of those diagonal entries. So in our little diagram, these are the squares. So this was really easy to calculate, much easier to calculate than if we had a non-triangular matrix. So it would be really nice if there were some way to get our matrix A to look like a triangular matrix. So then we could just calculate the determinant by taking the product of those entries on the diagonal. And how do we know how to do this? Well, if we do row operations, we can get A looking like that. In fact, that's not even all the way down to reduced row echelon form. So we already know how to do that. So it'd be nice if we could come up with a way where when we're doing our row operations to get A down into row echelon form, we could keep track of what that was doing to the determinant. And in fact, there is a way to do that. So let's think about what our row operations are. We have three row operations: replacement, interchange, and scaling. So let's take a look at what each of these does to the determinant. So if we do replacement, this is the one where we take a multiple of one row and add it to another row to make a new matrix. Let's call it matrix B. Then what happens? Well, the determinant of our new matrix B is going to be, in fact, exactly the same as our original matrix. So we can do row replacement to our heart's content and never change the determinant. If we do interchange, we're just swapping two rows. And when we do that, every time we swap two rows, we're going to introduce a minus sign. So once we swap two rows, our determinant is negative of what it was before. Our last thing that we can do is scaling. So we can multiply a row by some scalar k. And if we do this, then the determinant of our new matrix B is just going to be k times the determinant of the old one. So here are our three row operations, and we see what each one does to the determinant. Let's take a look at how to do this in an example. So this example is problem 6 from section 3.2, and it's asking you to find the determinant. One thing that I didn't mention in the last video, a notational thing, is if you have a matrix where instead of brackets or parentheses, you have vertical bars on either side, that's asking for the determinant. So when we say find what looks like a matrix but it has vertical bars there, we really mean find the determinant of that matrix. So I went ahead and in the blue, got us down to a more reduced form. So we have a triangular matrix at the end. So let's take a look at what this does to the determinant each time. So here's our original matrix. Let's call this A. So the determinant for this one is just the determinant of A. This is what we're trying to find. Okay, and to get from here to the next step, we did a row replacement, which doesn't do anything. And then we also scaled the first row by a third, and that does do something, right? That scales our matrix. So the determinant of this matrix, oops, somehow we lost a number there. Sorry about that. This was a -3. Okay, so the determinant of this matrix is going to equal a third of the determinant of our original matrix because we scaled the first row by 3. Okay. Then what did we do? Our next step was row replacement. Row replacement doesn't do anything. So the determinant of this matrix is the same as the determinant of the one before it. And the determinant of that one was a third of our matrix A, which is what we're trying to find. And then we do one more row replacement. So again, the determinant of this is still 1/3 of the determinant of A. So maybe let's call this final matrix B. So we have that the determinant of B is going to equal to 1/3 the determinant of A. And the determinant of A is what we're going to try to find. So let's go ahead and solve for that. So that's 3 times the determinant of B. But B is a triangular matrix. So we can go ahead and just multiply those diagonal entries. So we had a 1, and a -8. So this is going to equal -24. Okay, so pretty straightforward. So you'll notice as we're doing this that the only way for a determinant of a matrix to be 0 is if one of the entries on the diagonal is 0 in row echelon form. Why is this? Well, the determinant in row echelon form is going to be the same as the determinant of A with the addition of some scalar multiplication and some negation. But the scalar multiplication is never times 0. So if the determinant of A is 0, then the determinant of your row echelon form also has to be 0. And the only way for that to happen is if one of the entries on the diagonal is 0. So what does that mean? It means that the reduced row echelon form of A would not be the identity matrix if the determinant were 0. So this gives us a new theorem. A square matrix A is invertible if and only if the determinant is non-zero. This is great. This is what we wanted from the get-go, right? Because this property is what we have for 2x2 matrices, and we were trying to make determinants so that we could generalize that property. This also means that the determinant being non-zero is another property in our invertible matrix theorem, because that's the same thing as saying A is invertible. So our book calls this property T. We left off our list with R, so it looks like we've skipped S, but we'll get to property S later. So property T of the invertible matrix theorem says that if your determinant is non-zero, then all of those properties are true. The same as we can do row operations, we could also do column operations. So column operations introduce the same changes in determinant. This is not super relevant except for the fact that it tells us that the determinant of any matrix A is the same as the determinant of its transpose, because the rows of A are the columns of the transpose. So if you ever want to know what the determinant of the transpose is, it's the same thing as the determinant of the original. And our last property here is that if you have two matrices and you multiply them, then the determinant of the product is the same as the product of the determinants. So you could either multiply the matrices and then take the determinant, or you could find the determinant of two separate matrices and never have to do matrix multiplication. So this finishes off our properties. So I'm going to do another couple of examples just to show how the properties are going to work. And then we'll call it a day. So this is example, say 22-ish, problem 22-ish from section 3.2. The reason is I just changed a couple of numbers so that the arithmetic was a bit better. But what the problem wants you to do is it wants you to use determinants to see whether that matrix is invertible. So in other words, it wants you to find the determinant, and if the determinant is 0, then it's not invertible, and if it's non-zero, then it is invertible. So let's start. Here's our matrix A. Right here, and this is the determinant that we want to find. So this one will have the determinant, okay? And then what did we do to get from the first step to the second step? We swapped the first two rows. So that means that the determinant here is going to be negative the determinant of A, because we swapped those rows. And then to get from that step to the next step, we just did row replacement, which again doesn't do anything to the determinant. So the determinant here is negative the determinant of A again. And then to get from here to here, I went ahead and scaled that second row by 1/2 so that the 8s matched. And so what does that mean? Our determinant here is going to be 1/2 of the determinant before it, and the determinant before it was negative determinant of A. So now this determinant is going to be minus 1/2 the determinant of A. And then to get to our last step, we just did row replacement. So again, that doesn't do anything. So the determinant here is, again, going to be minus 1/2 the determinant of A. And let's go ahead and call this matrix B again. So what this means is the determinant of B, which we can easily find because it's a triangular matrix, is going to be minus 1/2 the determinant of A. So if we're actually trying to find the determinant of A, this would be -2 times the determinant of B, and the determinant of B is just the product of those diagonal entries because it's a triangular matrix. So let's see, 8 times -3 is -24, times -2 would give us 48. In particular, this problem didn't want us to find the determinant. It wanted us to see whether A was invertible. And this determinant is 48, which means it's not 0. So that means that our matrix A is in fact invertible. Okay, let's do 2 more examples. Our first one is to find the determinant of this matrix. And you'll notice, if you look hard enough, that this matrix is actually A transpose, where A is the matrix from our example that we just did. So I guess we call that 22-ish. So what does that mean? Well, we know that the determinant of a transpose is the same thing as the determinant of the original, and we just calculated that determinant in the last example. That was 48. So we're done. Our last example asks us to find the determinant of these products, or of the product of these matrices, and we could go ahead and multiply those and then find the determinant from scratch, and that's totally fine if you want to do that. Otherwise, you might notice that this is from problem 6, so that was that first example we did, and this was the matrix from problem 22-ish, which was the one we did on the last page. So we already found these determinants. This one's determinant was -24, I want to say, and this one's determinant was 48. So if we want to find the determinant of that product, then we could multiply them, or could multiply the matrices and then find the determinant of that, or we can just multiply the determinants of each of the component parts, and that equals a very big number. Okay, so to recap, if we're trying to find the determinant of something, we can do it from scratch the way that we did in the last video, or we can try to get it into row echelon form or into a triangular matrix and use those row operation properties and see how that affects the determinant. So that's a bit of a shortcut, if you will. We also saw that if the determinant is non-zero, then the matrix is invertible. And if you want to take the determinant of a product of matrices, you can instead do the product of the determinants. So as always, you are welcome, if you have questions, to email me or sign up for my virtual office hours.